So I think the first few slides do the KL divergence, which we did so far. And now we can talk about, one thing about KL divergence I forgot to tell you, and it is here. So this is the thing that we will be interested in. So our KL divergence will be with respect to the probability pi theta in the policy gradient algorithm. So you can fix one theta, and this is what I'm saying. If you fix one theta and vary the other theta, you get a function of KL divergence. Right? So this is the function that we are interested in. So this function, obviously, at this particular choice, the fixed theta naught, it will be 0 because KL divergence at theta 0, pi theta 0, or p theta 0, p theta 0 is 0. Its gradient at that point will also be 0. Why? Because f theta 0 has a minimum at theta 0. So its gradient is also 0 from the information inequality. And you remember KL divergence is expected value of some log thing. So if you took the Hessian of that log quantity, it turns out to be the same Hessian as the log quantity of the score function as we define the Fisher information. So I could have derived that, but let's just now focus on the slides. So this function that you get from KL divergence, it's Taylor expansion. The Taylor expansion of KL divergence itself comes down to being the Fisher information matrix up to order 2. Okay, the Taylor expansion of the KL divergence is just up to order 2, the Fisher information matrix. This was one of the things. That's why slides are good, because you forget about some detail, right? I would have probably, if I was doing through the slides, then I would have not forgotten it. It would have shown me this information. Anyways, so this is the new thing that we are going to do today. And there is before we do it for our particular example, there is a whole subject and a whole technique in how you reduce variance. It's called importance sampling. The importance sampling is the same thing. You want to find your problem, suppose, is to find expectation of f with some probability measure p. So you want to find in our language we write this like that. But this is hard to find, suppose, or this has a lot of variance. Okay, if this has a lot of variance, what do? You change the p by multiplying it by a function L, whose integral is 1. So replace p by PL, a new probability measure, where L is always greater than or equal to 0, L is always greater than 0, almost everywhere, and L p equals 1. So you just change your probability measure. Okay, and then you try to compute the expected value in this new probability measure of f over L. And sometimes that has a lower variance. So if you want to reduce variance, this is a technique that is classically there. So it says, don't do your integration or you compute integration. What you're interested in is this integration, so with respect to this probability measure. But you end up actually doing sampling with respect to a different probability measure, because that one is easier or whatever. So this is a classical idea called importance sampling. Okay, so we're not going to go through the detail, but the same idea will show up in the next slide for our for our, yeah, okay. So this is basically our problem now. Sorry, I need to keep this. So on the top of the slide is the problem description. The problem is we collect data with one policy. So, you have your robot, your program, anything out there in the world, agent. Somebody is right before you, right? That's the data you have. How did they graduate? What job they did? What relationship they have? Whatever. You have that data. You don't have the data of your life, right? And now your job is to say, how can I change my policy depending on their policy? Right? But their policy was in a different environment. Their policy was in a different time scale. Their policy had followed a different trajectory than where you are. So in reinforcement learning, the trajectories are going to be different. They depend on the policy. The trajectory does depend on the policy. So how can you go away with it? But still, at least mathematically, you could try to rewrite your objective by multiplying and dividing by the probability of the old policy. Just multiply and divide by the probability of old policy and take the expectation that should get rid of this multiplying and dividing. And that is a way out of saying, okay, now I can sample from the old policy and try and predict information about the new policy. Okay, so this is the main idea. Okay. So in particular, I think in the next slide, there is the gradient in two different forms. But this is nothing special about this slide. You can compute the gradient, and if you expand out the numerator and denominator, you'll see that the only terms that remain correspond to the actions. So sum of actions or actions depending on how so there are two choices of J here, and I think I realized when I was writing, I made a mistake of interchanging the two J's. So one J is with the sum of actions, of policy action divided by policy action, and one is without the sum. But they are both valid choices, but they're different. Valid but different objectives. And the derivation in either case is the same. So, but I think one has to be consistent, at least writing it out. But in implementation, you can choose one of the two J's. It's the same. So the question is, if I want to answer the question about how the other policy will change, depending on the data of my current policy, how valid is my data? So if I want to implement changes in my life, depending on somebody else's life who has lived before me, can I actually go 500 years back, 5,000 years back, and try and say, oh, I can live my life the same way as he or she did? Apply the same policy. It's probably not going to work because my trajectory is very far from the trajectories of that agent, of that policy. What you want is a trajectory, is a policy that is close enough to your policy to be able to imitate from the data. And what can we use to say two policies which are probabilities are close enough? What will you use? You will use here divergence. So that is the simple solution, simple-minded solution. The first solution is the following. Let me just be sure. Now I'm confused about where. Okay. So I think I made a philosophical statement somewhere there, which I also noticed now. Bad policies collect bad data, right? So if you use current data to move policy in slightly wrong direction, that policy will actually will go away from the optimal. It's not like supervised learning where if you have a wrong step size, the new data will correct the step size. You will eventually get to converge to the solution. In the supervised learning, the data is stationary. It's fixed. You have a collection of data. So if you make a mistake with your step size, the addition of the data will correct your mistakes. But in reinforcement learning, data is not fixed. It depends on the policy you work with. You will get your new experience based on the policy you work with. If you go worse and worse policies, they will provide you worse and worse data. So, for example, my agent is here and I want to execute some process of walking in this room, but my policies have moved on to agents that are in some other planet doing some other thing, and what they are doing will not apply to me anymore. What they observe, what their obstructions are, what their environment is will not apply to the current agent. So that is what is meant by bad policies, collect bad data, because they are far away. They're collecting data on the moon, and I want data here. So how is it going to work? Okay. So this is the solution to that is to always say that I will pick new policies that are within a certain KL distance from my policy that I fixed, that I am working with. So this determines my range of step size. How big a step size is allowed? I can choose another theta as long as I'm not going too far away in KL divergence. So this is essentially the only thing that you need to know in trying to implement this surrogate or this importance sampling kind of idea to policy gradient algorithms. Okay, so you can apply the data from the old policy as long as you're within certain KL divergence distance. And this delta is a hyperparameter. It will depend on your problem, of course, what you should choose. Okay. So this is the algorithm. I think it's written out there. So you want to maximize the same objective that we wrote down, but within the constraint of. So if you put theta prime equal to theta in this objective, actually, you will recover the policy gradient method. If you prove theta prime equal to theta, it will improve the theta zero probability. Sorry, if you prove theta equal to theta zero in this notation, then it will tell you how to improve the theta zero. But currently, you're collecting data with theta zero, and what you want to improve is a different policy. You want to improve the theta policy, okay? And it can be done as long as you're not going too far in KL divergence. So that is the idea of TRPO algorithm. So I think maybe we are also not. How much time we have? Okay, then. So if you're familiar with constraints, so this is the problem that was there in the last slide, is a constraint optimization problem. It's optimize something provided a constraint on KL. And there is a solution to such problems in calculus. What's the calculus solution? The Lagrange multiplier. So I suppose most of you have seen it at least once. Lagrange multiplier. But maybe I could put some comments in somewhere. So it is a classical way of actually there is just a lot of exercises that one does, a lot of problems that one solves this way. All constraint optimization problems are almost all real constraint optimization problems are solved using Lagrange multipliers. Okay. Which says that you take a multiple of the constraint from your objective and define that as your new objective. And then you have to find not just the values of your x, parameter theta that will optimize this, you will have to also, in addition, to optimize it with respect to the parameter beta. So now you have added one more parameter to your optimization space, namely the beta parameter. So you can convert a constraint optimization problem into a normal optimization problem by adding a new parameter. Okay? So that is, but in certain cases, you can fix this parameter, compute it, fix it, and then you can just say maximize or that. So these are two ways of looking at it. It's not always easy to implement this. So the TRPO method is in principle good, but it is not always easy to implement it in this generality, because how are you going to compute this KL? Actually, I should have written the computation for KL on a slide, but I think I had decided to do it on the board. It's very easy to compute the KL formula, actually. So maybe I'll see if we can do it next time. So you should not worry about this KL part. We can write a formula for it. And I intended to write it on the board, but I think in 5 minutes it's too late. Okay. So the scale part can be computed. It's not such a big deal. But the thing is, it's still not an easy algorithm to converge. And what one can do is the following. So instead of the KL divergence term, you take the Taylor series expansion of the KL divergence. I cannot even say Kullback-Leibler divergence. And the Taylor series expansion will, up to order 2, will only contain the Fisher information matrix. So in the previous constraint optimization, in the previous optimization problem, you just replace the KL divergence term with the Fisher information matrix that you can actually compute from different methods. There are various methods to do it. Okay, so that gives you a second order approximation to your problem. So the policy gradient method was a first order approximation to achieving a better policy, but it has a lot of variance. And this is now a second order approximation because it's now approximating your objective by a second order differentiation. The Fisher information matrix is a second order derivative. So you can say you have now, after Taylor expansion of order 2 approximation of your problem, and that will be a better solution. But it depends on your implementation. Sometimes these things are easy to compute, and then they are indeed quite efficient. Okay, so that is how you use the scale divergence in comparing different policies, getting a constraint optimization problem, and then using the constraint optimization problem, you just approximate it. Again, from the knowledge of how the KL divergence differentiates. And that's it. That's a nice enough algorithm to be implemented. All right, so I think that's too fast, but that's it for today. All right, and let's just stop.